As you may recall, in the last lecture, we were talking about the line spectra of various elements. So as you may recall, we have an experimental situation where if we take a gas in a tube, and the gas is at a fairly low partial pressure, and we hook this up to a high voltage source, that if the light emitted by the gas is directed through a prism, we will get bright line spectra. And these spectra will be very different depending on the element that is being used in the experiment. So as you can see here, if you do just a little analysis on your own of these various spectra, you will see that lithium is very different from sodium, is very different from potassium. So a question that scientists had is, why do we have these line spectra with these very specific wavelengths in the visible light spectrum, as opposed to something that it was, the familiar experience of the continuous spectrum of light emitted by the sun? So this was a puzzle for scientists, and they started their work not on these more complex line spectra, but actually on the hydrogen atom. Scientists chose to work on the hydrogen atom, it being the simplest atom to work with. It only has one electron. It has a fairly clear-cut line spectra ranging, as you see here, from 4 lines starting a little over 400 nanometers and extending to a bit over 650 nanometers. In 1885, Johann Balmer actually derived an equation that used full integers to calculate the 4 visible wavelengths of light emitted by hydrogen atoms. However, it turns out that there were other discrete lines for the hydrogen atom outside of the visible light range, found in the UV and IR regions. So Johannes Rydberg picked up Balmer's work and actually generalized his formula to explain not only the visible light line spectra, but also the line spectra occurring in the UV and IR regions. So he derived the formula that you see here on the slide, and it is 1 over the wavelength equals a constant, R, known as the Rydberg constant, times 1 over n initial squared minus 1 over n2 squared. This is perhaps a little mysterious to you. What are these n's? Well, we're going to be talking about them a lot more. Ultimately, in terms of their being described as energy levels for electrons. The main thing to take note of right now is that they are integers, and therefore can describe the line spectra since they allow the calculation of a very specific wavelength rather than as opposed to a continuous spectrum. The Rydberg constant itself is a very tiny number. It is 2.18 times 10 to the negative 18 joules. And Rydberg could calculate this very precisely because he had very good data, and using this formula he was in fact able, as mentioned, to explain or to calculate the discrete lines of the hydrogen atom that are generated across the electromagnetic spectrum. Now, this was tremendous progress, what Balmer and Rydberg had done, but there were still a lot of questions. And one problem that existed was for any atom, the model of the atom was that we have a nucleus, of course, consisting of protons and neutrons, and the idea, according to classical physics, was that the electron was in orbit around the nucleus, but not at all restricted to any particular area, just kind of whirling around in an elliptical orbit in a planetary or solar system type model. There are a lot of good reasons that doesn't work. One of which is, according to the laws of classical physics, this would mean that the electron would ultimately annihilate itself in the nucleus. The reasons for that are a little complicated. You can read more about it in the book, but let's for now just say it didn't work. So Bohr said, okay, I'm going to try to bring together some of the ideas of classical physics, but I'm going to combine them with the ideas of quantization. And the findings that, as you recall, we said the energy of a photon equals Planck's constant times the frequency. So the idea that the energy of a photon, and now by extension the electron, is proportional to its frequency. So let's take a minute to talk about that. Photons are these kind of unusual particles about which we have not really pinned down their physical properties. Electrons, on the other hand, are particles that we understand perhaps a little better. They have a mass, they have a charge. So now we're talking we've moved on from the photon and we're talking about the electron. But we're also talking about the relationship of what the electron is doing to photons and to visible light. Because as we saw, we know if we really heat things up, elements or metals, they will ultimately emit light. So this question and the mechanics of this question is still being worked on by Niels Bohr, a very famous Danish physicist. So what did he propose? Well, he proposed that the electron can only have these specific quantized energy values. So here we get back to n equals 1, n equals 2, n equals 3. We can now think of these as energy levels, and that the electron can only move between these discrete energy levels. So the idea here is that light will be emitted as an electron moves from one energy level to a lower energy level. So a higher to a lower energy level, a photon will be emitted. Well, Bohr basically confirmed the equation that Rydberg had developed, doing things slightly differently. And this was yet another step forward for understanding the behavior of electrons and forwarding this idea of quantization and its relationship to how elements emit light or other forms of radiation. Now, let's take a moment to think about energy levels and how this relates to some of the fundamental laws of physics. And one quite important fundamental law is that matter is the most stable when it has the lowest possible energy. So if we're going to talk about these energy levels, we should understand that an electron when an electron is in the lowest energy orbit, this kind of restricted area, the atom is said to be in the ground state, therefore the most stable. On the other hand, if the atom takes up some energy, let's say we bombard it with some kind of electromagnetic radiation, then it is possible for the electron to move from a lower energy level to a higher energy level, which we would call the excited state. This means that an atom can potentially absorb energy from electromagnetic radiation in the form of a photon, so that the electron moves from an orbit with a lower end to that of a higher end. Conversely, let's say the electron has gotten excited, it's not going to stay in that state. It's going to have a tendency for the electron to return from the higher excited end state to the lower end. And that is when the atom is going to emit energy as a photon. So since delta E, our energy, can only have discrete values, as we just described in the equation relating energy to integers, the photon absorbed or emitted can only have a wavelength with a discrete value. This is something you might have to think about a little bit and go back and look at the Rydberg equation, which was confirmed by Bohr. He came up with exactly the same equation, and think about why this is true. So what was achieved is it explained the line spectra. It really confirmed and explained the line spectra for the hydrogen atom in mathematical terms. The bad news for the Bohr model was it could not explain the line spectra of multi-electron atoms. We're not going to be able to go into that very deeply, but just a couple of the flaws related to the fact that Bohr's model was still based in laws of classical physics that did not hold up entirely, and also his model did not take into account the fact that electrons repel one another. So these were great strides, but there was still a tremendous amount of work to be done to develop the field of quantum theory and to continue to explain some of the phenomena that were being observed. In spite of the limitations of the Bohr model, let's revisit this idea that when an electron falls from an excited state at a specific energy level to a lower energy level, that it will emit light in the form of a photon or a whole bunch of photons. So we can see this here in this figure. We could have the electron dropping only a single energy level, and the energy of the photon emitted would be described, as always, by this equation, E equals Planck's constant times the frequency. Of course, if there is a more significant drop in energy levels, if the change is from, let's say, n equals 3 to n equals 1, then we're going to have a larger energy change, and that will be reflected in the equation E equals hv, or h nu rather. So one of the things you're going to be asked to think about is relating these changes in energy level of the electron to the wavelength. As we know, E equals h nu, but E also equals h times the speed of light over lambda. So you're going to get a little practice thinking about that and how these various equations relate to one another. Let's take a look now at this figure, which is a representation of changes in energy level when the electron in the hydrogen atom drops from a higher energy level to a lower energy level. So if you focus your attention on the left-hand side of the figure, you see that at the very bottom we have the ground state, which is n equals 1, and this ascends through the energy levels up through n equals 7 all the way potentially to infinity. We have different series here representing different transitions between energy levels. We have the Lyman series, the Balmer series, the Paschen, and the bracket. We're going to focus some of our attention on the visible light series, seeing as how that's what we talked about originally with the hydrogen atom. But we're also going to revisit the equation that we have already talked about, which can give us the energy of the photon, the delta energy, and the relationship of energy to the Rydberg constant times 1 over the square of the energy level. Notice that we can calculate this for the energy level of the final state versus the energy level of the initial state, and consequently we can get delta E. So how does this relate to our figure? Well, let's take a look. You can imagine that potentially the electron in the hydrogen atom might descend from the level Ni initial equals 2 to N final equals 1. This takes place in this first series. Alternatively, it could happen that the initial energy level could be 3 and the electron could descend to a final energy level of 1. If we're talking about the Bohr series, we have the possibility of something like Ni equals 3 initial state to Nf equals 2 final state. As you can imagine, if you considered all the possibilities here, they are quite multitudinous, but no matter which one we look at, we have the ability to calculate the delta E between one energy level and another. This is a useful exercise, and you can also notice that depending on the difference in the energy levels, we could have a much larger energy change. For example, if we go from initial state 7 to final state 1, we're going to have a very large energy change. Whereas if we looked at something like going from N equals 5 to N equals 4 in the bracket series, we could have a fairly small energy change. So you'll be putting this formula to work in the very near future. For the various series that we just looked at, I'd like you to note that depending on the series, the behavior that is being described is in various regions of the electromagnetic spectrum. So for example, the Lyman series is in the ultraviolet range, whereas Bohr is in both the primarily the visible, but also a little bit in the ultraviolet range. So you may want to go back and look at that figure just so you understand a little better how these different series explain the emission spectrum in the hydrogen atom, depending on which one we're talking about. We're now going to put our formula to work on a practice problem where we're going to figure out what the wavelength of a photon is in nanometers when in the hydrogen atom a photon is emitted during the electron transition from the Ni equals 5 state to the Nf equals 2 state. In terms of tackling this problem, we've actually been asked for wavelength. But notice that the first thing that we can actually do, given the problem itself, is that we can calculate the energy of the emitted photon using this formula. Once we have gotten at the delta E, we can then solve for the wavelength of the photon using the fact that E equals Planck's constant times frequency, and the fact that the speed of light equals lambda times frequency. This is going to involve a bit of rearrangement, but it's all quite doable, as you will see. So here you see that if we simply plug the numbers in, we get a delta E answer, which is going to be negative 4.58 times 10 to the negative 19 joules. Now, clearly we can't have really a negative number for this emission process because wavelength and energy are not negative numbers. Well, I shouldn't say energy, but wavelength is never a negative number. So in any event, let's now that we have 4.58 times 10 to the negative 19 joule, we can use that. Now we're going to have to think about doing some rearrangement because ultimately we need to solve this problem for wavelength. So since we have solved for delta E, we could take our equation delta E equals Planck's constant times frequency and rearrange it to solve for frequency. In other words, frequency equals delta E over H. Now if we take the formula lambda equals C over frequency, and we sub in for frequency delta E over H, that ends up being E equals speed of light times Planck's constant over delta E. Notice because we subbed in delta E over H for frequency in the denominator, our final rearrangement is in fact C times Planck's constant over delta E. So when you solve this problem, you will get the answer 434 nanometers, which, as you know, is in the visible light spectrum. An interesting thing to note here is that if we were to look at this specific transition of n numbers, this is in fact within the Balmer series, which describes visible light. So our answer lines up with what we learned about previously. In quantum theory, it is definitely true that one question leads to another. So the next question on the horizon for physicists was, why is the energy of an electron quantized? Enter a gentleman by the name of de Broglie, who in 1924 reasoned that if photons can have, or light can have both particle and wave-like properties, then electrons could also exhibit both particle and wave-like properties. So in order to support this wave idea, he came up with a mathematical equation to describe this behavior, which is 2 pi r equals an integer times the wavelength, which he ultimately developed into wavelength equals Planck's constant over mass times velocity. Now notice we're talking about the electron, which is a very different creature from the photon, which is actually not considered to have any measurable mass, whereas an electron does. So de Broglie's equation actually incorporates both a term for mass and for velocity. Getting back to the integer point, let's focus our attention for a minute on these figures. And notice that an integer has to be incorporated into an equation that describes a wave-like behavior for an electron, because it has, the electron is circling around the nucleus, and it has to be an integer number of wavelengths in order for a standing wave to fit into an orbit. So if you look at the top part of this figure versus the bottom part of this figure, that becomes a lot clearer, because we can see that an integer number will fit nicely into this electron orbit, whereas a non-integer number would not. We're now going to put the de Broglie equation to work in two different scenarios where we're dealing with a so-called particle. So in case A, we're actually going to be dealing with a tennis ball. And we're going to be asked to calculate the wavelength associated with that tennis ball. Remember, we proposed that particles moving at a certain velocity are also going to have a wavelength. So here our tennis ball is traveling at 68 meters per second. It has a mass of 6.0 times 10 to the negative 2 kilograms. And we're going to use that to calculate its wavelength. In case B, we're going to calculate the wavelength actually associated with what we've been talking about, which is an electron, a somewhat smaller mass than the tennis ball, 9.1094 times 10 to the negative 31 kilograms, moving at also 68 meters per second. So what is going to be our result? We're gonna find something rather interesting here about how very different these results are going to be, and the extent to which they're dependent on the mass of the object under consideration. We have the data that we need, so essentially this is going to be a plug-and-play operation using the de Broglie formula. A couple things to note, however, are that Planck's constant is represented in joules dot second. So this means that mass and velocity have to be in kilograms and meters per second. That's in fact what we were given in the problem numbers, but I just want you to know why this is important. It is important because 1 joule is that is in fact equal to 1 kilogram meter squared per second squared. So this will mean that our units all line up. We can plug the numbers in using the Broglie formula, lambda equals Planck's constant over mass times velocity. And when we do, we're going to get 1.6 times 10 to the negative 34 meters. This is a very, very tiny wavelength. In fact, it's so tiny that it is a wavelength that cannot actually be detected by any existing measuring device. In the second case for the electron, we're going to see that we get a very different result. When we plug the numbers in, because the mass of the electron is so tiny and the mass is in the denominator, we're going to find that we actually get a much larger wavelength. And if we convert this wavelength, which is 1.1 times 10 to the negative 5th meters, to nanometers, we get 1.1 times 10 to the 4th nanometers. This is in the infrared region and in fact shows that only electrons and other submicroscopic particles do in fact have measurable wavelengths. Sneak preview, we're going to pick up next time with the Heisenberg uncertainty principle, which is a formula that describes mathematically that it is impossible to know simultaneously both the momentum, which is defined as mass times velocity, and the position of a particle, such as an electron, with certainty. There is the mathematical formula that you see here to describe this behavior. And if you take a look at it, you'll see that if delta x, we can pin that down with increasingly certainty, we are less able to pin down delta p. That means the closer we get to identifying the position of a particle, the less certain we are about its momentum and vice versa. The other equation of interest is the Schrödinger wave equation, which is a very complex mathematical function that we'll talk about not in great detail. The main takeaway is going to be this is an equation that is known as a wave function, and it is in fact was kind of a revolutionary equation, and it's going to help us understand that we can describe something called atomic orbitals, which will give us the probability of finding an electron in a volume of space, in particular for multi-electron systems. So I will see you next time in class.